Okay, I think that we are ready to start. So hello, everyone, and welcome to the electrochemical colloquium. Today, we're discussing electron transfer at the electrochemical interfaces and Frumkin correction. As you know, the electrical double layer, where all the electrochemical reactions occur, can be very, very complex. And so understanding how the potential and, of course, the associated electrostatic fields are distributed within the double layer is super important for the correct modeling of electrochemical reactions. And so our today's speaker is Professor Galina Tsirlina, who is a widely recognized expert in electrochemistry and charge transfer processes. Galina received her PhD from Moscow State University in 1985 and habilitation degree in 1996. She also spent several years at Frumkin Institute of Electrochemistry. And since 2001, she's a professor of electrochemistry at Moscow State University. Galina, thank you so much for joining us today. The stage is now yours.
Oh, thank you, Andrei. Dear colleagues, I am very happy that organizers of this colloquium were interested in the topic which I consider as my favorite topic during all my life. And what I'm going to present today is a part of my long-term joint work with various groups. And there are some key collaborations, I think starting from 90s, first of all, Renat Nazmudinov from Kazan, then Ron Fawcett from UC Davis, and late Alexander Kuznetsov, our great theoretician from the Frumkin Institute of Electrochemistry. My talk will be divided into two parts. The first part will be partly historical, but really it is very important that to say 80 or 90 years ago, a number of fundamental things were done, not only by Frumkin School, but by other people. The topic was hot during that period, and we shouldn't forget about it. And I shall try to remember you some most important things which were done during that period. I shall pay special attention to reactions complicated by strong electrostatic repulsion, which are mostly known as anions reduction at negative electrode surface, because these reactions give fantastic possibilities to verify modern theory of the elementary act of electron transfer. I shall also tell you some things about the possibilities and prospects of molecular modeling in relation to the bridge between experiment and theory in this field. And after a short period for questions, I shall go to some more advanced topics, probably more close to comparison with modern theory, with real physics. And I hope that these points will be of interest for people who do not work in the field of traditional electrochemical kinetics, but who deal with, to say, some fundamentals of molecular electronics. So I shall start from the very old story to tell you what does it mean, slow discharge theory. Really, slow discharge is the idea which looked fantastic before 1920, because everybody was sure that electron is always transferred in a very fast step, and any electrochemical reaction cannot be limited by electron transfer. The idea of slow electron transfer, slow discharge, was first discussed in relation to hydrogen evolution reaction, for which the first step is always hydrogen discharge. And in the well-known work of Vollmer and Erde-Groos, it was demonstrated like this electron transfer. And jointly with preceding work of Butler, this Vollmer and Erde-Groos work gave us the equation, which is well known up to the modern time, which you all know as Butler-Vollmer equation, and occasionally, and probably the name of Erde-Groos disappeared from this title. And this is a starting point. It was important phenomenological equation, which also explained the empirical equation proposed earlier by Tafel in 1905. If you simply go to say 50 millivolts from equilibrium potential, one of these exponents becomes very small, and you can limit yourself by only one exponent to say for cathodic reaction, and this will give you Tafel equation. What experimental data were considered in relation to this equation? Mostly the data for hydrogen evolution on various metals, and the main comparison with experiment was Tafel constant B, which was shown to be close to 116 millivolts at room temperature, corresponding to alpha transfer coefficient equals 0.5. What was the next step done by Frumkin only 2-3 years after Vollmer and Erde-Groos? And it is also named slow discharge theory, but in contrast to Butler-Vollmer equation, it contains important term which belongs already to real physics. It's real physical theory. It's electrostatic term, which in international literature is typically named Frumkin correction. And in Russian literature, this equation is still considered as the main equation of slow discharge theory. This is a sort of Tafel equation. I mean that it is far from equilibrium. So only one exponent works. This exponent with potential is here. And correction consists in two things. The reactant is considered as a point charge or uniformly charged sphere, which is located at some plane parallel to the electrode surface. This plane is assumed to be equipotential, so there are no local electrostatic interactions. And the potential of this plane was first considered by Frumkin as zeta potential. You should remember that Frumkin was not electrochemist during his early period of his career. He was the expert in interfacial phenomena. He was close to colloid chemistry. And this zeta potential was a sort of available information about potential in the diffuse layer. Slightly later, Frumkin changed it for psi prime potential, and this psi prime can be considered as Guy-Chapman potential at the outer Helmholtz plane if the center of the reactant is located at this plane, or it can be shifted from this plane, and in this case you can also calculate using Guy-Chapman theory, which gives the dependence on the distance along the normal to the electrode surface. So as the reactant is located here, not here, the electrode potential is corrected for this potential in diffuse layer. This is the first correction. Here is it. The second and very important correction is related to reactant concentration. You know that if the reactant is charged and the electrode surface is also charged, concentration in this plane, in the reaction layer, never equals concentration in solution bulk. It can be calculated assuming electrostatic nature of the work of reactant approach simply by Boltzmann equation like this. And this will be the work term, the work of reactant approach, defined using this electrostatic potential. So to use this equation, you should put reactant concentration just in the reaction layer, not in solution bulk. Of course, this equation assumes transfer coefficient about 0.5. Here is it. And this means that Bremsted behavior of the system is assumed from the very beginning. This is the main problem of combining this consideration with modern theory, which goes beyond Bronsted, and we shall discuss it mostly in the second part of today's colloquium. And finally, the assumption was that the rate constant, here is it, is over voltage independent, which means that it is independent on the electrode charge as well. This is also very doubtful approximation, and we shall discuss it in detail at the end of the first part of this colloquium. What was available for verification of Frumkin's idea? In contrast to Vollmer and Erdős, he could not use the data for many solid metals, and because even if kinetic data were okay, there were no reliable double layer data. It was only one electrode material which provided both kinetic and double layer information during that period, and this material was mercury. Fortunately, Herovsky school made a lot of advancements working with mercury electrode, and in particular, Herovsky school studied hydrogen evolution, because when they worked on polarographic analysis, they had to study hydrogen evolution as bi-side reaction. They had precise data, and one of important persons who worked with Herovsky during that period was Gerasimenko, Ukrainian person, a brilliant experimental person, and just the data of Gerasimenko were used in 33 Frumkin's article to compare the calculated over voltage at given current in solutions of various supporting electrolyte concentrations, because you all understand very well that this zeta potential, which we later started to name psi prime potential, it strongly depends on supporting electrolyte concentration. He used that data from Gerasimenko and Schlentek. Here is this famous article, and he got very good, not exactly quantitative, but semi-quantitative agreement with experimental shift of polarization curves in solutions of acid of various concentrations. What is another important point, I think, in this 33 Frumkin's work? It is the most early model of reaction layer which I ever met for electrode reactions. Probably somebody met earlier models, but I think that this was the first one, when the number of ions in the reaction layer. A number of ions at the plane formally corresponding to the closest approach was estimated and compared with the limiting coverage. And you see that the values are very realistic and very close to what we can calculate today. This took place 90 years ago. During that period, Frumkin had no his own experiment on electrochemical kinetics. He only started with experimental electrochemistry in this aspect because everything what he was doing earlier was to measure electrocapillary curves and to do some things related to electrical double layer. But just in 1933, he joined Moscow University, Karpov Institute in Moscow, and his teams, both in university and in Karpov Institute, started with electrochemical kinetics at the second half of 1930s. The most important person who worked out the techniques to measure precise polarization curves in various ultra-pure solutions was Zinovy Iofa. Zinovy Iofa, this name unfortunately is less known to international community. It was probably slightly screened by Frumkin's name, but I want you to know that this was a person who educated several generations of electrochemists of Frumkin school. Very important person was also Serafima Levina, who worked in Karpov Institute. I am citing here a number of early works on electrochemical kinetics, which were done directly under Frumkin's supervision. Frumkin never co-authored the works if his participation was limited to discussion. So you do not see Frumkin's name here. And I separate this person, Valery Zarinsky, who later worked in electroanalytical chemistry, because at the next picture, I want to show you one illustration from Zarinsky's thesis. This thesis defended in 1938 contains a very detailed scheme and procedure of measuring polarization curves of hydrogen evolution. And this was done in a style which I never met during all my life. Purification of mercury and purification of solution was done separately in special devices. And these vessels with mercury and with sealed, and they were mechanically broken to put these pure substances directly to the cell, which was already deaerated. Hydrogen was always used for deaeration. It was very pure hydrogen with catalytic purification. And using this type of experiments, it was possible in 1930s to measure the currents up to about 20 nanoamps without any contribution from residual oxygen. Really, I am very surprised because during all my life, I met very few examples when these low currents were available. And it is a special story how these glass cells with numerous modifications to prevent penetration of oxygen to solution, how they were constructed, and what the brilliant glass blowers worked with these devices. The experiments of Levin and Zarinsky allowed to go to much lower current densities as compared to what was available in Hiroshiki school, and to verify Frumkin theory in a very wide range of potentials, also in the vicinity of the potential of zero charge, which was surely very important. Now I would like to retranslate Frumkin equation to more modern terms. It's completely the same what was written at the initial slide, where the equation from 1933 work was copied. This is the interfacial concentration of the reactant calculated by Boltzmann formula. This is corrected potential. And finally, these terms containing potential in the diffuse layer, they are combined into one exponent, which contains transfer coefficient and the charge of reactant. We use this O because it is an oxidized form, and this is written for cathodic reaction. So we have two exponents, one governed by electrode potential and another one governed by potential in the diffuse layer. This allows to propose the procedure of linearization of polarization curve. If instead of usual Tafel coordinates, we use corrected coordinates. This procedure is named corrected Tafel plots. It was proposed in '61, much later than Frumkin started to work with this electrostatic issue. And I shall show you this work slightly later. But in any case, you see that going from this equation to coordinates where current is corrected for psi prime potential and electrode potential is corrected for psi prime potential, we expect linear dependence if we still trust in linearity, if we still assume Bronsted behavior. How to find this potential? We have no microscope to see in what plane near the electrode the reactant is located. But we can start from, to say, outer Helmholtz plane, then to calculate the potentials at various distances from this plane, try to put this potential for correction in both left and right part, and see for what distance we obtain the same dependence using the data for various supporting electrolyte concentrations. The obligatory point is to have the data for various supporting electrolyte concentrations which strongly affect this psi prime value. This procedure was used many times. And basically, if we are successful, if we obtain the data for various supporting electrolyte concentrations coinciding, and if we have the linearity, we have determined both transfer coefficient and exact location of the reactant. This was the main idea. Of course, it is very important to have predominating contribution of the first exponent to check whether this model works. This contribution becomes predominating just for reactions which go under conditions of strong electrostatic repulsion. This can be anions reduction at negative electrode charge. In this case, when we go to more negative potentials, we increase over voltage. So this second exponent increases the current. But simultaneously, we go to more and more negative potentials in diffuse layer. So this exponent decreases the current. So they fight with each other. And if this exponent is strong enough, and it is strong enough in diluted supporting electrolyte solutions, it can even give stronger effect on the current. And we can observe the situation when the current is decreasing with over voltage, which is very unusual, and probably one cannot believe that it is possible, but experimental evidence exists. Where this can happen, where this first exponent can win, this can happen in very diluted electrolyte solution in the vicinity of the point of zero charge. Here is my notation for the point of zero charge, because here the potential in the diffuse layer increases in a very fast manner with electrode charge, which means with potential. Later, when we go to the charges about 7 or 8 microcoulombs per centimeter square, we have quasi-logarithmic behavior of potential in the diffuse layer. And here the second exponent will always win. But this place is the most interesting. The idea itself, I think it was evident to Frumkin and people who worked with him already before World War II, because there were some attempts to study the anions reduction and the negatively charged surfaces. But the first success appeared much later, in 1949. And the author of this discovery was Tatyana Kryukova. Tatyana Kryukova is a very important person from polyrography. She learned polyrography in the 30s, and she worked in the Institute of Analytical Chemistry and Geochemistry during some period. And she was dealing with polyrographic analysis of strong oxidizer, peroxide disulfate. It was a complex set of data. Here at positive electrode charges, here is the potential, it goes to negative values. At positive electrode charges, we can see nothing because we have a strong polyrographic maximum. But at negative electrode charges, we observe and the degree of this inhibition depends on supporting electrolyte concentration. Here is the limiting diffusion current. So when we go to higher supporting electrolyte concentration, we already do not see the pit, even if it exists, it is screened by diffusion limitations. But for diluted solutions, we see it very, very well. Sodium sulfate, and the concentrations are millimolar here, millimolar. This anionic pit is a famous thing which we shall discuss now, because it was studied for various types of anionic reactants and gave very quantitative results. The phenomenon itself is interesting from several points of view. First, it is the type of negative differential resistance. Second, and it is the sequence of the first, this can result in very interesting current oscillations, which were later observed. But I think that the most interesting point for electrochemical kinetics as a whole is that we can observe the dependence of current on potential without diffusion limitations in essentially wider potential interval than usually, because we have inhibition just at the moment when diffusion kills our kinetic observations. To show you another example going from Girst, it is cation oxidation on the positively charged surface. Again, all the voltage increases, positive potential in diffuse layer increases, and two exponents fight with each other, and a peak is observed. But now when we go to more positive potential, this is the reaction of oxidation of europium-2 cation. Schematically, it looks like this. If we have no repulsion and no attraction, we have usual Tafel behavior. This can be observed in concentrated supporting electrolyte, where electrostatics is screened by ionic atmosphere. Then, if we use modulated electrolyte, we already have some repulsion. And for anions at negative electrode charges, we have the currents lower than expected in the absence of repulsion. For modulated solution, even more lower, and so on. And when we go to the most diluted solution, where the potential in the diffuse layer is especially high, I mean the absolute value, and increases very fast with potential, we have current decrease, and we observe the peak. We cannot observe the picture of this sort in the real experiment, because sooner or later we meet diffusion limitations. So what we observe in experiment is just the lower part of this picture. Here I show the data, and in diffusion current is not horizontal simply because tension charge, and so the dropping period changes with potential. But we see just this picture, which we cut by this limiting diffusion current. The quantitative results on reduction of anions of various types were collected by several persons from Frumkin school, and one of very important persons was my teacher, Professor Petri, who was Frumkin's PhD student. And they worked jointly with Frumkin the technique how to treat the data, because they always considered the possibility of participation of ion pairs, not of bare anions. So they worked out very interesting technique how to determine the charge of reacting species in solution bulk. And then using this charge, it was possible by considering the cross sections for various supporting electrolyte concentrations at constant electrode charge. Here is it. And then they constructed the corrected Tafel plots. And the most important finding was that these corrected Tafel plots coincided very well for various concentrations of supporting electrolyte, points of various types here, but were different for supporting electrolytes with different cations. This is like cationic catalysis, which we always meet in the kinetics of homogeneous reactions. And it was some mystery which indicated participation of these cations in electrostatics, and indicated that there were some local electrostatic effects as well. Very important person from electrode kinetics, Delahaye, formulated in '67 that the corrections for for the concentrations in the plane of closest approach and the drop across the diffuse double layer, this is just the essence of Frumkin correction. They are already okay, that they work that they can be made quite well. But really, I think that Delahaye was too optimistic. Because even in the first work, his own work on corrected Tafel plots, he announced some quantitative failure of the double layer correction. It failed to work quantitatively. It worked very well for anions reduction because it allowed to obtain monotonic corrected curve from non-monotonic initial polarization. It even allowed to have the same results for several metals with different points of zero charge. But it was impossible to explain this problem with cation effect. And so ion pairing and some non-local models of electric double layer were, of course, required to continue with this topic. This was the last Frumkin's article on anions electron reduction, 75. He passed away in 76. And he insisted on necessity of consideration of ion pairs in this last article. Basically, Frumkin's idea, Frumkin correction, was able to explain this anionic pit, which is, of course, very important as any qualitative effect. It was able to explain supporting electrolyte concentration and the effect of metal nature in terms of metals with various points of zero charge. But these effects were still under discussion. And very important experimental fact was zero activation energy measured from temperature dependencies in the pit. This zero activation energy was interpreted by Frumkin as just the effect on ion pairs, which were destroyed at higher temperatures. Really, I think that this is, at least for some anionic reaction, manifestations of activationless discharge. Three most studied anions were hexacyanoferrate, peroxide disulfate, and platinum-2 chloride. They all demonstrated cationic catalysis and completely different shapes of corrected Tafel plots, including rather exotic shapes. What we tried to do with Rinat and with active participation of Ron Fawcett, we first tried to propose more quantitative corrections, assuming the real molecular structure of the reactants. The most impressive, just because, again, it shows qualitative effect, the most impressive is the possibility to have repulsion or attraction for neutral reactant depending on its location near the electrode surface. This was done with example of hydrolyzed platinum-2 aqua chloride complex, for which electrostatic effect depends on the orientation. Either it is oriented with negatively charged chloride or with positively charged protons to the the closer the atom to the surface, the higher is the contribution of its sign of charge into the total work of approach. I shall not stop on the details of this calculation, which probably were partly naive, but of course they allowed to understand what can be the effective charge of the complex reactant with inhomogeneous charge distribution along the coordination sphere. This was continued jointly with Ron using various complex species like amino complexes and cyano complexes and aqua complexes and so. And of course, the resulting corrected Tafel plots were strongly dependent on these electrostatics induced by inhomogeneous charge distribution. For non-spherical reactants, it was also important to account for various possible orientations at the surface. Then we addressed the idea, which is very close to discreteness of charge, which Ron also addressed during many years, and there were some ideas going from theoreticians concerning local interactions in the other layer. It allows to use two components of the Birkhoff approach, one going from non-local electrostatics and another one going from this local interaction of anion with cation located at the outer Helmholtz plane. This allowed to explain to some extent the difference between cesium and sodium supporting electrolytes for peroxide disulfate. Here is it. Here is peroxide group, and for hexacyanophile. We also tried to go step by step, changing the distance between the electrode and reactant, calculating this molecular psi prime effect and substituting it in equation for corrected Tafel plots. And if we still trusted in linearity, this allowed to determine the transfer coefficient, rate constant, and also the distance of this closest approach. I mentioned this works with references, but I know that it is very difficult to fix the references during colloquium, so I shall be happy to send these references or this presentation to everybody who are interested. Do not spend time now to try to fix these numerous citations. And we also considered multi-charged reactants. Now I show you for the first time the reactant which I like very much and from which we shall start in the second part. This is polyoxymetallate containing cerium 4 central atom, which can be reduced at potentials much more positive than the ligand starts to reduce. So we can have long distance electron transfer. But like all polyoxymetallates, this anion is multi-charged, and of course it cannot react as 8- anion. It is linked to numerous cations, and we were lucky to find a way how to calculate these stability constants for this associated species, and we compared it with experimental data on ionic association, because our friends from St. Petersburg, Konstantin Michelson, great person in ionometry, in potentiometry, helped us with this determination. So we have a set, due to Renat's efforts, first of all, of various computational methodologies to see the reaction layer from these molecules. I am already more or less close to the end of my first part, and I would like to attract your attention that 5 years ago, when we celebrated the jubilee of Journal of Solid State Electrochemistry, I wrote a small review which collects, by the way, many references mentioned above and some others. And I want to show you one illustration which I used in this review. This is Frumkin's Ex Libris. Here is Frumkin's last name in Russian. And you see all the symbols which we have here in the sky above mountains. Frumkin was very enthusiastic with mounting. All these symbols are just from this slow discharge theory, from this Frumkin correction idea, which we considered now. Electrode charge, supporting electrolyte concentration, over voltage, psi prime potential, so on. Unfortunately, the molecular details of reactants and reaction layer present not the unique, not the exclusive complication for going further with this Frumkin correction concept. Another very important complication consists in the fact that some other parameters in the equation for current are also depend on the electrode charge. And in the mid-90s, it became already evident due to very active work of Sluyter's group. I cite here all these brilliant works, which were done mostly with galams and amalgams. And we discussed with Margaret many times how it works. It was evident that the pre-exponential factor, which means rate constant in Frumkin's equation, it depends on the electrode charge. It was also a theoretical prediction in '94. And it was a very serious discussion between Margaret and theoretical people. And we also participated in this discussion to some extent because some estimates in this theoretical paper induced a number of questions. But the fact is evident. Pre-exponent depends on the electrode charge, simply because the electron tail goes to longer distance outside the edges of atoms, and the overlap increases. And we also had experimental result of this sort. It was published in later than Sluyter's results in '98. It was concerning chromium complex with ethylenediamine tetraacetate, which was reduced on metals with different points of zero charge. So the total dependence on the electrode charge, it is minus of course, consisted of several parts for several metals, but it was evident that rate constant can increase at least several times in the range of charges, to say from 0 to 15 microcoulombs per centimeter square. I would like to mention that our first paper with discussion of this effect was dedicated to Lev Isayevich Kristalik, who unfortunately passed away recently, and we always shall remember him. So now I mentioned serious complication going from several factors depending on the electrode charge. We are forced to solve a sort of crossword when we deal with these parameters with simultaneously affecting the rate of the electrode process. This was my first part, and I shall be very happy to answer your questions. And if some questions cannot be answered briefly, I would like to continue later by email, and you can use my email to formulate your questions as well. Thank you very much.
Thank you so much, Galina. I'm letting the audience ask. So please feel free to raise your hand or ask the question directly. Maybe I can start in that case.
As usual.
Well, not as usual, sometimes. So if we go to the slide 14, I think this is where I got quite curious about this overall approach. So you mentioned that, yes. So if we look at the plot on the right, so you mentioned that this is, of course, the way that we can check the local, the role of the local electrostatics, right? And
we cannot check, but we can assume that it is important. Yes.
Exactly. That's what I mean. So would you say that this is the best way to do this? So we should plot corrected Tafel plots and then say, yes, there is some effect of the from the local electrostatic fields from the cations, for example, in this case, or there's no effect because for example, in CO2 reduction, recently there were quite a number of papers claiming that the cations have this additional catalytic effect, but certain types of cations, certain charges, certain sizes. So is this the way that one can say that, yes, indeed, they do play a role? And can we say how big of a role they can play?
You see, first they can play two different roles. The first role is ionic association in solution bulk. Mm-hmm. In this case, you simply have, if you have stronger association with cesium, which is very typical because ion pairs with cesium are not solvent separated and they are stronger. In this case, you simply have for cesium very high contribution from reactant with the charge -1 instead -2. Of course, the repulsion is stronger for -2. And this allows solutions with cesium to show higher currents. This is the first trivial idea. Another one is this local interaction in reaction layer. Basically, you always have two parallel reactions with cation, with ion pairs and with bare anion. I have a series of works which I do not cite here because you know they are very technical, in which it is considered how to construct corrected Tafel plots under conditions of two parallel reactions. It is not so trivial, and we were dealing with it for a very long period. But later we understood that it is much more effective simply to try to imagine how it can be with interfacial pairs and how it can be with pairs in the bulk, and then to compare with experiment. Mm-hmm. The first step should be qualitative. It is important to find strong qualitative effect in experiment. If the effect is small and quantitative, we cannot check anything reliable. Too many uncertainties.
Mm-hmm. And if it's strong, then we can.
If qualitative effect is strong, you see, if you model this cesium effect in a layer, and you see between cesium and sodium, which is several orders of magnitude, can be explained by this effect. This is okay, you can forget about bulk. If not, you should return to the idea of bulk pairs and to consider parallel reactions.
Okay. Another question, it might be rather basic question, but I think since we have a lot of students, it's very important to ask basic questions. When we look at the anion, the reduction of anions on the negative electrodes, how does it happen? We have a negative anion, we have a negative electrode, so they seem to be somewhat repelling each other, right? So maybe you can just comment on that.
You know, it is a typical mistake which many people do when they tell that anions cannot go to cathode because they must go to anode. This statement is related to migration effects, to transport effects. But what we discuss here is simply equilibrium concentration, this one.
Mhm.
Very low equilibrium concentration of anions near negatively charged surface. It is low, but it is non-zero. And they react, because if one assumes that anions cannot be reduced as a cathode, one should forget about galvanics at all, because the majority of galvanic processes operate with anionic reactants for metal, for cathodic metal deposition.
But this is mostly outer sphere reactions, not inner sphere. There's no absorption, or at least there are some cases, of course, when absorption happens too.
You see, this electrostatic repulsion partly guarantees the absence of specific absorption, because it, at least at higher negative charges, it partly decreases. But there is one situation, this one with platinum chloride, which tends to adsorb strongly. And it is not completely deleted from inner sphere at layer, even at rather high electrode charges. This is the reason why the anionic pit for platinum chloride is so deep as compared to other anions. But in real solutions, in the absence of very high external chloride concentration, it is hydrolyzed. And adsorption is not so strong, and we observe more usual behavior. There are, of course, some anions which tend to adsorb specifically, but sooner or later they are deleted from the negatively charged surface.
Okay, thank you. We have a question from Wolfgang Schmidt.
Yes, I just wanted to make a short comment on this. The deposition of positively charged metal ions often takes place on positively charged electrodes. Silver deposition takes place on positively charged silver, or does the deposition of copper. So that is quite common.
Wolfgang, first, I am very glad to see you here.
And I'm very glad to hear you and see you.
Yes, and you and Elizabeth as well. Wolfgang, you know, there are many versions of metal deposition. Of course, these noble metals you mentioned, they react on positively charged surfaces. But if we deposit it from complex electrolytes, which is not so rare, you know, silver or gold are deposited from cyanide complexes, and or they were deposited before it was forbidden ecologically. Yes. And in this case, the equilibrium potentials are shifting strongly to more negative values because the complexes are strong, and we have the reactions at negatively charged surfaces.
But I think an important point is the deposition of lithium on lithium. The lithium ion is always deposited on negatively charged electrodes, and we believe that this is the reason why it forms dendrites.
Yes, non-noble metals, of course, even without complexations, they all are deposited on negatively charged surfaces. But in this case, there are no repulsion because they are cations. And it is less interesting for this situation because in this case, both exponents work in the same direction. And the most interesting situation is when they compete, you see?
Yeah. In the case of lithium, Elizabeth and I believe its important point is when you have a small tip of lithium on a lithium electrode, you have a very high negative charge just on the tip. And this will attract the positively charged lithium ion, and they all go towards the tips. And we believe that this is the reason why they form dendrites. But okay, just some propaganda for our point of view on this. But the main point is very often you have the deposition of metal ions, positive metal ions on a positively charged electrode, and the opposite also happens. And this has an effect on the sort of structure which the deposits take.
I think it's a very important comment.
Thank you.
Okay, I'm thinking that if we have no more questions, maybe we can proceed. And then we will have another question session later.
Can we proceed?
Yes, yes.
So, dear colleagues, starting this part 2, I want to explain my personal attitude to the interaction of theory and experiment. And it is very important for me that several great theoretical persons are here now. Probably they disagree with some comments and discuss it later. I think that experimental people are responsible for experimental verification of this. I think that this situation is not symmetric. Theoretical people always go further. And they have done a lot for us. And we still cannot verify everything what was written by them. A situation which I want to present today in relation to this point, it is activationless discharge. It is important in the context of theoretical events which took place in the very beginning, when Professor Marcus invented his brilliant theory and extended it to electrochemical reactions in 1965. And in parallel, De Ganadze with co-authors in the theoretical department of Frumkin Institute, this was department headed by Benjamin Levich, they worked out the important points of the theory of heterogeneous reactions, and in particular, they proposed how to account for participation of various electron levels in the electrode in the region which corresponds to Marcus inverted region. I would like to explain that it was very important finding, which was never addressed by experimental people seriously, simply because it was very difficult. Frumkin correction, which I told you about in the previous part, remains the same for any theoretical approach which we apply, because it is simply correction for electrode potential and for reactant concentration, and both parameters can be found in any type of the theory. What I show you here is the most general expression for the rate of electrode process, which accounts for participation of electrons of various energy. They find themselves in Marcus quadratic term, and participation of the reactants at various distances. Usually, we do not use so complex equations because we simply do not know how to deal with them. What we typically do, we ignore participation of any electrons, excluding from the Fermi level. And we ignore participation of any reactants, excluding that one located at the closest approach, and we simply use some effective parameter like reaction volume, and we put it to say 1 angstrom and do not think about it seriously. When this becomes important? This becomes important when we go far from the equilibrium, when we have mid and high overvoltage, when we have the reaction energy, which already corresponds to the vicinity of inverted Marcus region. And these electrons start to participate in heterogeneous reaction. And we need to account for them here and here. And we have the region, which is named activationless, which corresponds to the current not depending on the free energy. For homogeneous reactions, the inverted region corresponds to decrease of reaction rate, and for heterogeneous reaction, it basically corresponds to the plateau. We tried to apply some models beyond Bronsted. First of all, Marcus theory, to consider the procedures which are the same like Frumkin correction, which was shown in the previous part for usual Bronsted type behavior. These anions, which undergo repulsion, were the most important participants of this story, just because they allow to have a wide range of electrode potentials, which is not complicated by slow diffusion. Again, it is impossible to do with reactions of other types, where we always have the interval of 200 or 300 the highest. So I shall start from this cerium polyoxymetallate anion, this large associated with cations, really having the charge of about -2. We studied all details of its ion pairing, so we understood what species we have in the reaction layer. And this anion also demonstrates anionic peak, which depends on supporting electrolyte concentration. Here is the limiting current. It has rather specific behavior at positive electrode charges, but this is just due to strong anion adsorption. And today I shall not discuss this point. I shall discuss only this region. It is wide enough, about 0.6, 0.7 volts. So it was possible to see how the behavior of this anion corresponds to Marcus theory. We simply reconstructed the corrected Tafel plots to corrected Marcus plots. We have done the same. We constructed these coordinates. You see, this square root results from quadratic term. Instead of rate constant, unknown pre-exponential term appeared here. It is unknown. This is the same, the value which depends on the distance near the electrode surface. And here is reorganization energy. Why these corrected Marcus plots are much more reliable as compared to corrected Tafel plots? Because in frames of Marcus theory, we're not only sure that the curve should be linear. We also have important criteria. Both the intercept and the slope depend on one and the same parameter, on reorganization energy. So it cannot be arbitrary ratio between the slope and the intercept. Exactly. Then we worked with the Frumkin. Assumed various orientations of our reactant and various geometric locations near the electrode surface. We calculated work term for the species, assuming that the potential in the diffuse layer is distributed along this axis. Then we calculated effective psi prime, effective psi prime potential from this real Vekov approach. Substituted it to this equation and tried linearization. If we have something looking like linear, we checked whether the criteria with lambda works. If not, we changed the geometry. If yes, we considered it as possible result. This procedure resulted in several possible dependencies, not completely linear, but some of them are close to linear. They correspond to various pre-exponential factors. The highest is here, it cannot be higher. It is a special story to explain. And from this set of data, we cannot obtain the exact value of parameters, but we have obtained very narrow interval in which this parameter can lie if the story corresponds to Markov theory. This interval is as follows: that the pre-exponent can be changed in the interval less than 1 order of magnitude, which is not so bad. And reorganization energy can be, to say, from 140 to 160 or so. This is not so bad accuracy. And this is a very large anion, so the solvent reorganization energy is low, of course. And our construction results in transfer coefficient, which demonstrates completely normal Markov behavior. There is some uncertainty in the value. You see, it can be varied from, to say, 0.23 to 0.27, but it is a narrow interval of possible parameters. It is much better than the uncertainty which we have with corrected Tafel plots when we try to do them linear, but we are not sure that they must be linear, you know. This procedure is even more important when it does not work. For this polyoxymetallate, it worked and it gave the result. But for classical anions, like peroxide disulfate, which are reduced at extremely high over voltages, this procedure does not work. And this means that the situation is beyond usual Markov theory and just correspond to activationless region. Really, for peroxide disulfate anions, the equilibrium potential is about plus 2 volts versus normal hydrogen electrode. It is very, very high. So the real over voltage is more than 2 volts, 2 or 2.5. And for any sets of parameters, for any assumed geometries, for any assumed electrostatic work terms, the curves constructed in the coordinates of corrected Markov plots demonstrated non-monotonic behavior. And this is just the feature of activationless discharge, which starts somewhere here at over voltages above, to say, 2 volts, 2.2 volts or so. This is very important story because it is a diagnostic of activationless behavior. I should tell you that this story with activationless region, it is very, very old. What is the feature of activationless region? Alpha is assumed to approach zero asymptotically. For activationless discharge, it is assumed to approach zero asymptotically. In contrast to homogeneous reaction, when alpha continues to decrease in a linear manner, intersects zero and goes below, and this is already inverted region. The people observed very, very low values of transfer coefficient for hexacyanoferrate reduction. And this observation was done already in 1959, just by Oleg Petri, who studied this anion in terms of his diploma work, diploma thesis. The corrected Tafel plots for hexacyanoferrate always demonstrated the trend of slope, very serious slope decrease. Of course, there were uncertainties. The uncertainties which I told you about. How many cations are attached to this hexacyanoferrate, how it interacts with cations in diffuse layer. So one can hardly indicate the exact value of this transfer coefficient, which goes from traditional treatment. if you simply construct corrected Tafel plots with the real charge of bare anion, you will have. If you prime F distribution in this species, you obtain lower transfer coefficient.
I'm sorry, Galina, can you repeat again the last 30 seconds? I think we had interruptions.
Okay. I told that various values of transfer coefficients can be obtained. Is it okay now, Andrei?
Yes.
Yes.
That's perfect.
Various values can be obtained under various assumptions about reaction layer. For usual corrected Tafel plots, we obtain 0.2. If we consider real distribution of charge in the reactant, we are lower, about 0.1. If we consider participation of ion pair, we obtain already below 0.1. This is the uncertainty of usual procedure. But let us not try to fight for quantitative value. Let us simply consider the polarization curve as a whole. Frumkin equation, which is based on Bronsted behavior, assumes that polarization curve, when we go to negative electrode charges, should look like this: peak and increase. Peak when the first exponent wins, and increase when the second starts to win. If we calculate from Marcus theory, assuming very high voltage and low reorganization energy, we expect something like this. This is already an inverted region. If we use Levich-Deganadze-Kuznetsov approach and account for participation of non-Fermi electrons, we obtain activationless behavior like this. This curve goes down slightly only because of increasing electrostatic repulsion. In the absence of repulsion, it is expected to be horizontal. And here are experimental points. And I think that this picture is very simple for conclusion. Really, for this reactant, we have activationless behavior. This is hexacyanoferrate, the classical reactant. And I insist on the fact that activationless discharge was really observed very early, but was not noticed. Then it was the first experiment with hexacyanoferrate. Then it was observed directly because of this very low alpha, and was not noticed again. This is just Petri-Frumkin period. Then I remember myself how many people, including Lev Isayevich Kristalik, were looking for some reaction with activationless discharge. And when I was a PhD student, I liked to visit Lev Isayevich in the institute, and he always told me that I must look for activationless hydrogen evolution on tungsten carbide or so like this. So people were looking for something, but they already had. Now there are no we had many interesting ideas about it. For example, that it allows to do something like electronic spectroscopy because it must be sensitive to the electron levels of the metal, and even invented the title Faraday spectroscopy, but it was never realized. Of course, it is very important for electrochemical kinetics in STM configuration, which we could not imagine during that period. And I also rely on the fast progress of computational electrochemistry to clarify many molecular details and to make this situation around activational discharge more certain. Now, I would like to explain why these interesting reactions of anions reduction under repulsion conditions were not recognized as activationless discharge. First, this, the shape of polarization curve was completely different from that people expected. Then for these anions, we always have either the region of mid over voltage or the region of high over voltage, but we can hardly observe low and mid and high simultaneously, because you have seen, like for peroxide disulfate, low over voltages are completely masked by slow diffusion. And on mercury, they are also masked by polarographic maxima. So we do not have all wide over voltage region. We have only some parts of that region. But in contrast to usual reactions, we have mid and high over voltage region. It's of course important. Then there are many uncertainties in double layer models and in the models of reactants, because reactants are multi-charged, multi-atomic species, and they are complex enough. And it took some time to understand what to do with these corrections. We still have problems with bulk equilibria, I have already told you. So we have many problems which prevented recognition of this important phenomena at the initial stage of the study of these reactions with repulsion. It is also a basic problem for comparison with the theory, because for real reactants, we cannot find immediately the exact values of parameters which we can put to theoretical equations. We go step by step, and computational work is a very, very important bridge to accomplish this. Now I would like to go to the problem which just forms this crossword. Not only the charge of electrode, but also the distance is parameter which affects many factors in any equation for the rate of electrode reaction. Distance affects the closest approach. It determines the reaction volume, which will be a topic of special discussion during my last part of this colloquium. There are also the problems with interfacial ionic association, which basically a sort of specific adsorption, and with specific adsorption as is. There are also the problems when sorry. There are also the problems with solvent reorganization energy, which depends on distance and depends on sometimes depends on the electrode charge. And of course, I already told you that the reactant electrode overlap also depends on the electrode charge, and surely it sharply depends on electrode distance. It is very difficult to deal with dependence of current on voltage, ignoring the problem of charge and distance as multifactorial effects. And one of the most interesting problems in this story is just the problem of reaction volume, which combines inside one value several basic quantities depending on the charge and distance. What is the definition of reaction volume? Reaction volume can be determined as the integral of reaction rates for reactants located at various distances z. Z is now the axis normal to the electrode surface. And if we integrate over z, and then normalize to the value which we usually consider the current for reactants as the closest approach. Here is it for outer sphere reaction. Here is it for inner sphere reaction. Then we obtain this delta Z. People usually assume that the quantity demonstrating the most sharp Z dependence is just overlap, because it is exponential and the parameter is of the order of 1 angstrom. So this means that if these reactants and products are located 1 angstrom more far from the surface than the reactants as the closest approach, they already have 1 order lower contribution, and we can limit ourselves by this closest approach. But the problem is not so simple, believe me. There is a list of various parameters participating in various equations, and one and the same quantities participate in simple equations like slow discharge theory as used by Frumkin, and in Marcus equation, and in various equations going from other theories. Really, what Frumkin named psi prime, it is simply the work of approach. This is electrostatic component of the work of approach, and you can add the energy of specific absorption for oxidized form and for reduced form. So for reactant or the product, you can consider the work of approach instead of this psi prime. This is completely the same. If you want to introduce the correction for Tafel, which Frumkin used, you simply should use the equation for activation energy from Marcus theory, which will contain surely the difference of the works of approach of reactant and product. And if you substitute this sum by these two formulas written above, you will see that as the charges of reactant and product, the difference of charges is unity. This will be simply F psi prime in the absence of specific absorption. So this Frumkin's correction can be easily introduced in more advanced theoretical treatments. Z dependence is unavoidable for pre-exponent, for transmission coefficient. It is unavoidable for lambda, and we know very well from the formulas which Professor Marcus wrote for reorganization energy long ago. And these work terms are also distance dependent and of course charge dependent, both in the electrostatic part and in the part related to specific absorption. And all these contributions, all these Z-dependent contributions, which in their turn depend on the electrode charge, for example, this dependence becomes more sharp, they are inside this delta Z parameter. Inside this delta Z parameter. And I tell you about reaction volume now just because the anions reduction, which I have chosen today for majority of illustrations, gives very interesting example of reaction volume behavior. This example was discovered by Feldberg, and at the next slide I shall show you. First, we should list the trends which are induced by distant dependence of any of these parameters. This is decreasing dependence, typically exponential. This is increasing with distance. For current, the increase of reorganization energy will result in slow decrease And this depends on the type of adsorption, and because it depends on the electrode charge, it depends on potential. So there are contributions increasing and decreasing simultaneously. What Fehlberg invented, it is a very, very interesting article, which I consider as a very good exercise for students. He considered the reaction volume under conditions of reactant repulsion and attraction, ignoring the dependencies for reorganization energy, considering only the dependence for electrostatic terms and for pre-exponent. He used some reduced coordinates, but in any case, I shall show you. This is beta kappa ratio, means beta is the coefficient here, and kappa is inversely by length. Approximately, this corresponds to usual beta like 1 angstrom and 1 millimolar supporting electrolyte. There are many pictures in this Fehlberg article which correspond to other combinations of these parameters. And so we see here, when we have attraction, there is nothing special. The logarithm of the ratio of rate constants, which accounts for all distances, and rate constants for closest approach, which really means reaction volume, this is somewhere near unity or slightly lower. But when we have repulsion, it can increase dramatically several orders. What does it mean? This means that these closely located reactants undergo very strong repulsion, but their location is favorable from the point of view of overlap. Simultaneously, these reactants locating at longer distances have lower overlap, but much lower repulsion. And if repulsion here is very strong, they can be predominating participants of all the reaction. And this delta Z can be extended to the area of several or even many atomic sizes, molecular sizes. This is what we see in this picture. In reality, the picture is hypothetical. I calculated many times using this classical experimental data for anions electroreduction what part of these curves we can observe experimentally. For example, for peroxide disulfate, we can observe something like this interval. Here the reactance charges are too high. We do not have reactants with so high charges. And here the potential interval for the values of certain potentials in diffuse layer are not available. So we have a limited region. But we can expect that for anions electroreduction, the reaction volume can be several times higher, this is logarithmic scale, as compared to usual value of 1 angstrom, which we put without any special reasons when we calculate something without integration over Z. And really we tried to address this quantity more precisely.
Okay, we can wait maybe for
possible.
a bit. Galina, I think we've been having an interruption the last maybe 10-15 seconds.
Okay. My sound now. Is it okay? No.
A bit interrupting still, but it's better.
It's better. So
yes, now it's better.
Better. So we address this more in more molecular manner with Rinat Nazmudinov in the beginning of this century, and obtained some values which are really higher than this typical 1 angstrom. And finally, I would like to say that the problem of fixing the distance between the electrode and reactant, and by this means to fix the values of all the parameters, not to deal with dependence on distance, to deal only with dependence on the electrode charge. It will be already a more simple story. A good way to do it is, of course, to put barrier layers of known size. And you all know that alkyl research is very wide, and it can be done, unfortunately, it cannot be done in non-aqueous solutions, but it can be done in aqueous, and as we demonstrated with Vika Nikisina, who is also here, I have seen, it is possible in ionic liquids as well, which is already not so bad. And we know that there are some very sharp exponential dependencies of reaction rate on the distance, which is to this alkyl delete the reactant from solution. You know that you have the reactant only at a single distance. It was the dream. But we found, and it is the last work which I mentioned today, we found when compared the behavior for attached alkyl attached reactants and reactants in solution which are reducing via these tile barrier layers, that everything is not so simple. We compared the dependencies of rate constants on the alkyl layer, and for some reactants of these constants distance, and for some, and we found that it is really impossible to explain this result, assuming the position of the reactant due to some tile conformation. This is the.
I'm sorry, Galina, would it be, I'm so sorry, but I think we've been having interruption for the last slide almost non-stop. So maybe if it's okay for you to explain it again.
Should I return to the previous slide?
Yes, the previous, just explaining again, because it was unfortunately again interrupted.
Okay. So we compared the rate constants for attached reactants and for reactants attached to alkyls, and for free reactants in solution, which were separated from the surface with the same alkyls. And we found that this difference can either decrease or can increase, demonstrating that for attached reactants, delta Z value also cannot be ignored. Andrei, Is it okay now with the sound?
Yes, it was very clear.
Okay.
Thank you.
And we explained this delta Z for attached reactants by conformational changes in the region of attachment of reactant, which is illustrated here. And I attract your attention to this recent article simply because it continues the topic and extends it to I think enough for everybody. Two of them are to fix. Is it okay now?
Yes, it's still a bit slow. Yeah, I think the last thing that we heard is that you said it's enough.
And I shall with reactants which are attached by their strong adsorption. And there are many types of polyoxymetalates for which we see a chance to get the results comparable with theory. I see very interesting alternative to alkantiles. They are layers with strong lateral interactions, which are not permeable for any reactants and cannot be deformed. This is adsorb layers like adamantane derivatives. I would mention that solvent effects are extremely important. Today, I told you nothing about solvent effects. It is another part of our joint work with Rinat Nazmudinov, but it is another story. Solvent effects are important to make a proper choice of theoretical relationship, to understand where you are in non-adiabatic or diabatic region or in the mid. However, this diagnostic tool induce new complications because you change viscosity and permittivity simultaneously. At this stage, I still believe that aqueous carbohydrate syrups are the best as compared to aprotic solvents. Finally, I want to stress that electrostatic interactions are, of course, very important in various layers, including inner sphere reactions like taking place in electrocatalysis. And of course, you mentioned today CO2 reduction, and I can mention oxygen reduction or peroxide reactions for which, to say on oxide catalyst, you have some charge distribution and also you have electrostatics. And the approaches worked out for outer sphere reactions, of course, can work at this stage. And two final remarks are simply some slogans which I usually formulate for myself. It is necessary to find various modal systems with one or another predominating factor, because there are too many factors and you cannot recognize them if they give the comparable effects. And of course, I stress that disagreement of experiment and the model is not so bad, because it is always informative and allows us to go further. I am grateful to colleagues from various places who joined the studies I mentioned today. There are many people, you can read the names here. And I think that we can go to discussion or questions if possible. Thank you very much for your attention.
Thank you so much for this very interesting talk. I think we're open to questions.
I do not see chat. Probably there are some questions in the chat.
I see Rudy Marcus.
Yes,
online.
I'm here. Can you? Oh,
Yeah,
let
we
me
can hear you.
unmute. Yeah, let me
Yes.
unmute.
We can hear you.
Yes.
Yeah, okay. Can you hear me now?
Yes.
All right. Well, this is Rudy Marcus speaking, and thank you very much for Galina, for that very interesting talk. I haven't been working very much in this field. I've been working largely in other fields. So it's good to hear what some of the developments are. Of course, there's also some emotional aspects. You mentioned Dogonatzi's name and Levich's name, and I remember fondly at the SITSI meeting in Moscow in 1965, and Dogonatzi asking me to come with him down to Georgia, where we would walk from village to village, drinking wine in the middle of the night. So I have many pleasant memories from there. And I do have some questions here or there, but I thought maybe I would ask them to you in an email. And
I shall be happy to receive your email.
Yeah.
Of course.
Yeah.
I shall wait for your email.
Yeah. There is one thing I noted recently. There was a publication that came out that claimed to have direct evidence of the image charge effect. And then when I tried to search for the publication again, I couldn't find it. So are you familiar with any recent work which claims to say, yes, we have definite evidence for the image charge effect? And one reason why I ask is that sometimes one sees in the literature that there can't be such effect because it would be shielded. But actually, one can't shield against both the charge, the distribution of the reactants and the distribution of the products at the same time. So it's an incomplete shielding at most that can occur. So I was curious whether you've seen a recent publication on that. But in any case, thank you very much for your lecture. And it's good to be brought up to date a bit.
Oh, thank you, Professor Marcus. I have not seen this work you mentioned, but I think it's possible to find, of course. And I think in correspondence, we can continue to discuss.
Wonderful. Thank you.
Okay, thank you. I think if we have no more questions, maybe I can ask a few.
Yes.
One is related to the state of the surface. So would you say that for many of the equations that you apply here, it requires to have a perfect surface, single crystalline surface or mercury surface?
Yes. Yes, of course, mercury is still unique to do the things of this sort, but mercury has another disadvantage. You need to work with dropping electrode, and so you are limited in time. And if you want to study something inner sphere, if you have some slow adsorption, you are simply not in time to reach the equilibrium. If to consider other metals, I think that gold is the most simple. I mean, preparation of more or less good interface. And of course, there are some articles going from Tartu, from Estonia, Jan Lust and others, who made very accurate things with SP metals like cadmium, cesium, bismuth, of course, and they obtained a lot of data for anions reduction as well. And by the way, Jan Lust was very active in applying our approach to this how to say, molecular psi prime correction, molecular Frumkin correction. But it seems to me that he was even more enthusiastic than necessary.
Mm-hmm.
But the data for solid electrodes exist.
Okay, and then relevant to this, in the community, a lot of people do Tafel analysis, especially for electrocatalytic reactions, right? So for somebody who's watching this talk from the side, they may think, okay, maybe we should switch to corrected Tafel analysis, Tafel plots. Maybe there's something you can comment on this as to what people normally do, especially for non-perfect electrode surfaces, for powders and so on. That is very, very widespread. And what you've been presenting here, which is sort of the fine type of analysis that requires perfect electrochemistry and perfect surface.
You know, not so long ago, in 2005, we celebrated 100 of Tafel equation. And dozens of articles were written about Tafel plots. And I wondered how specific reactions can be considered in these coordinates. And I really do not understand why. Corrosion people tried to construct Tafel plots for the electrodes, which surface is changing in the course of corrosion. In electrocatalysis, this is completely senseless because the potential dependent coverage by some adsorbate affects the Tafel plot. So I think that for majority of people, Tafel plot is simply a type of plot. It means semi-logarithmic plot, nothing else. It lost its initial content. But if to consider it in relation to electron transfer processes, in 2007, we published a paper also dedicated to 100 of Tafel equations, so we were late. And we considered just the factors related to elementary act, which can affect Tafel slopes, like ionosphere asymmetry, various types of reaction terms, and so on. I think that this article is probably of interest, and if somebody is interested, it cannot find itself, I shall send the text or reference.
Okay, thank you. Renat, go ahead.
Okay, so Galia, first of all, thank you very much for your talk, which was interesting for me, first of all, from the viewpoint of nice historical aspects, which you always discuss in detail. I have no questions. I have only a couple of comments. So the first comment is that recently we predicted nice AA effects considering the reduction of anions in nanoscale. I mean, when we can consider nano rods or nanotubes emerged in electrolyte solution, and we predicted great enhancement of the electron transfer rate. And then another interesting effect, which is the disappearance of the peat when considering the discharge of persulfate anion. I don't know, unfortunately, so far any experimental support, but the progress in this field is so impressive that I like to believe that in a while, in nearest future, maybe we can also some experimental evidence as well. That is the first comment. And the second is that probably a nice system is also, I mean, from the viewpoint of electrostatic effects on electron transfer, is the electron transfer in a tunnel junction when we have redox active species between the metal surface, like gold, for example, electrode, and STM tip, And you know that in this case, we have some challenging interplay between the bias potential effect and usual double layer effect. And it can be, in some version of theory, discussed in terms of two parameters, zeta and xi, which also affect greatly the shape of this famous bell-like dependence, current voltage dependence, and even on some quantitative values too. Okay, that's all.
This Renat's comment was contained in one line here. Thank you, Renat.
Okay, yeah.
Okay, any questions so far? No.
1 minute if possible. If there are no questions, I want to show this Frumkin's portrait. Probably some people here have already seen it. It is constructed from various electrochemical curves. Here is the nose from mercury drop, here is rotating disk electrode, and so on. And here is the main feature of his face is just this anionic pit. And here is hydrogen evolution. This is our symbolic picture, which still remains relevant. Even it was created in 65. It was 70 Jubilee of Frumkin. So thank you very much. I am prepared to additional questions now or by email, as you like.
Thank you so much, Galina. We've been here for 2 hours, so I think maybe it's good time to end our colloquium. So thank you again very much for a very fundamental and very insightful talk that we had on. We really like here electron transfer. So we've been inviting and will be inviting many speakers on this topic, various different aspects of electron transfer and ion transfer and other things. Thank you so much and have a nice day.